Let's take a look at the sampling distribution of the sample mean x bar. I'm going to assume that we are sampling from an infinite population, or that we are sampling only a small fraction from a finite population. This is true the vast majority of the time, but the underlying mathematics changes a little bit if we are sampling a larger fraction from a finite population. Suppose we are sampling from a population with mean mu and standard deviation sigma. And we're going to let x bar be a random variable representing the sample mean of n independently drawn observations from this distribution. And a couple of important points. The mean of the sampling distribution of the sample mean is simply equal to the population mean. Symbolically, the mean of the sampling distribution of x bar is equal to the mean of the population from which we are sampling. And the standard deviation of the sampling distribution of x bar is equal to this quantity down here. The standard deviation of the sampling distribution of x bar is equal to sigma over the square root of n. Why are these two things the case? It's not too tough to show mathematically, and I'll look at that in another video. One more important point, if the population from which we are sampling is normally distributed, then the sampling distribution of the sample mean x bar is also normal. Now we're going to bring these things together in some probability calculations, and we would standardize in our probability calculations in the usual way. So for a single value, if we have some random variable x, say, that's normally distributed, then when we are standardizing for a single value, we say that z is equal to x minus its mean over its standard deviation, and we've done that previously. But for the mean of n observations, when we're standardizing, we would do a similar thing. Z is equal to the sample mean x bar minus its mean, which just happens to be mu, over the standard deviation of x bar. And this is simply x bar minus mu over sigma divided by the square root of n. So if we're talking about the mean of n observations, we need to remember to include the square root of n down here. Let's look at an example. The number of calories in an order of poutine at a certain fast food restaurant is approximately normally distributed with a mean of 740 calories and a standard deviation of 20. If you're unfamiliar with poutine, it is french fries, cheese curds, and a gravy. Very tasty, but also not so good for you. At a certain fast food restaurant around here, it has a mean calorie content of approximately 740 calories, and we're going to say it's normally distributed with a standard deviation of 20 calories. And we're going to do a couple of probability calculations. What is the probability a randomly selected order has at least 760 calories? Well, if we let the random variable x represent the number of calories in a randomly selected order of poutine, then x is approximately normally distributed with a mean of 740 and a standard deviation of 20. And what we want is the probability that x is bigger than or equal to 760. And we're going to standardize this, and we've done this type of thing before. Where we standardize it, we said our z is equal to x minus mu over sigma. So no problem, we can say this is a probability that z is bigger than or equal to 760 minus 740 over sigma, which is 20. And this is the probability that z is bigger than or equal to 1. And so if we drew out our standard normal curve, because z has a standard normal distribution, and we went to our normal table, or a computer, and we found the area to the right of 1, we would see that this is approximately 0.159 to 3 decimal places. Now, a different type of question, what is the probability the mean of 9 randomly selected orders is at least 760 calories? This is fundamentally different because we're talking about the mean of 9 of these orders. So we want to know the probability that x bar is bigger than or equal to 760. And we're going to do a very similar thing to what we did up top, but we have to remember that our z is equal to x bar minus mu over sigma divided by the square root of n, because we're talking about x bar here, not a single observation. So when we standardize here, we say probability that z is bigger than or equal to 760 minus 740 over 20 divided by the square root of 9. This is the probability that z is bigger than or equal to 3, where Z has a standard normal distribution. So we draw this out. We have 0 here, we have 3 out here in this right tail, and we're looking for this area. This turns out to be approximately 0.0013 if you put that into a computer or you use your standard normal table to find that area. Now visually, here's what's happening. The solid line is representing the distribution of a single poutine. This was approximately normally distributed with a mean of 740 and a standard deviation of 20. What we found in the first question on the last page was this area, the area to the right of 760 under this distribution. But when we were talking about the mean of 9 poutine, the distribution is a little different. It's very similar. This distribution has a mean of 740, so the same mean as that of a single observation, but the standard deviation of the sampling distribution of x bar was sigma over the square root of n, and that was 20 over the square root of 9, which is simply 20 over 3. So the standard deviation of this distribution is less than the standard deviation for a single value, and we can see that because it has this higher peak and less area out in the far tails. And so what we found in that second question was simply this little bit of area under this dotted line distribution out to the right of 760. One last thing before I let you go. There is a very important concept in statistics called the central limit theorem, and the gist of it is that the sample mean will be approximately normally distributed for large sample sizes regardless of the distribution from which we are sampling. So even when we're sampling from non-normal populations, if we have a large enough sample size, the sample mean will be approximately normally distributed. And this is an extremely important concept in the world of statistics and probability, something that is deserving of its own video, and I have a video for that, but I would be remiss if I didn't at least mention it here.